Swayam Prabha. Digital India. Educated India.
So, welcome back to the next lecture. So, last lecture we finished with the equation of continuity and solving a very simple problem for a pipe flow where the discharges were given. So, we have seen the equation of continuity A1 V1 is equal to A2 V2. So, now we need to also see it in a differential form. This is the most famous form of the continuity equation. So, in Cartesian coordinates, the equation of continuity is written as del rho by del t plus del rho u by del x plus del rho v by del y plus del rho w by del z. These are the convective terms. Okay. For incompressible flow, the density does not changes with time, and hence the above equation is simplified as, and the rho can come out. It does not change neither with respect to x or the coordinate and time. Therefore, this can simply be written as, so this will go to 0, rho will come out, so it will become rho del u del x plus rho del v by del y plus rho del w by del z is equal to 0, and if rho is not equal to 0, it can be cancelled from both sides. So, this is the continuity equation in the differential form. Okay. All right. Now, talk about rotational and irrotational action. If we consider a rectangular fluid element of side dx and dy as in this figure, you see this is point A, this is point B, here point A, point B, and this is dx, this is the distance, this is the distance of the side dx, and this is the dy, this is a fluid particle. Okay. Under the action of velocities, for example, here there is a velocity a at a, it is u, and in the x direction and v in the y direction. So, on the side dx it is u and the side dy it is v. So, this fluid element can undergo a rotation, and a rotation or a deformation right now, we call it deformation, as we can see here. Okay. So, this will undergo some rotation, and so at point B the velocities, if we assume in this direction, it is changing. So, u is changing in this direction as del u by del y into dy, and similarly while coming from here this velocity is changing in x direction as del v del x dx. Okay, therefore, the u and v corresponding u and v velocities here will be u plus del u del y dy, and v velocity will be v plus del v del x dx. Okay. So, this fluid particle will rotate as it appears in the figure 8.p, and this distance is going to be del v del x dx into dt, if we are considering the rotation in time dt. Similarly, this will be coming from here multiplied by dt, and if this angle is gamma 1 and this is gamma 2. Okay. Gamma 1 here is angular velocity of element AB, which is equal to del v del x. Okay. Gamma 2 is angular velocity of element AD, that is del u del y. We can go back to this slide here. You see del v del x, okay, and this is del u del y as we have written. Considering the anti-clockwise rotation as positive, the average of the angular velocities of the two mutually perpendicular elements is defined as rate of rotation. So, this example we took to tell you about what actually is the rate of rotation. Thus, the rotation about z axis can be given as half into del Vx, del V by del x minus del u by del y, okay, because this is going to rotate, you see the rotation this direction, and because of this it is in this direction, and because of this it is in this direction. So, they are opposite to each other, that is why this negative sign. So, it is rotation in z axis half of del v del x minus del u del y, okay, all right. Thus, for a three-dimensional fluid element, three rotational components as given following are possible. About z axis, the rotation is given as half del v del x minus del u del y. Similarly, about y axis, its rotation is given as omega y, it is half del u del z minus del w del x. And repeating the same exercise in x rotation about x axis, it is given as half del w del y minus del v del z. So, these are the three components of rotation, okay, all right. Fluid motion with one or more of the terms omega z, omega y or omega x, okay. So, this is not omega z, this is omega x. If these terms are not 0, this motion where these omegas at least one of them is not 0 is called rotational motion. So, the condition is omega z slash omega y slash omega x should not be equal to 0. If at least one of them is not equal to 0, it is called rotational motion. So, twice the value of this omegas about any axis is called the vorticity along that axis, okay. You must have heard the term vorticity. Thus, the equation for vorticity along z axis is 2 omega z is equal to, so this is, if you remember, the omega z was half times this thing. So, this is the vorticity along okay. So, a flow now is said to be irrotational if all components of rotation are 0. So, that means omega x is equal to omega y is equal to omega z is equal to 0. This is the definition of irrotational flow, and this is what is, so let me write it more properly. Omega x is equal to omega y is equal to omega z is equal to 0. This is called irrotational flow. This is what we assume the water flow in most of our hydraulic engineering based application. We assume the water is irrotational, the flow in the water is irrotational. That is why this concept is quite important. You already know this because you have already done the fluid mechanics course, okay. So, exactly what I have written. Now, we will see a practice problem. For the following flows, determine the components of rotation about various axes. So, we have been given u is equal to x y cube z, v is equal to minus y square z square, w is y z square minus y cube z square by 2. So, we already know the formulas. So the components of rotation about various axes are omega z. You see here is given by, this is a standard formula that we have seen. So what we need to do is del v del x. So del v is not a function of x, so del v del x will be 0 here as it is written, or let me just take an eraser, it's so this one. So this is going to be, so I will bring back the pen. So this will be 0, right. Now del u by del y. So from here del u by del y is going to be 3x y square z, and this is what has been written here, and this 0 has been written here. Okay. So therefore, which implies omega z is written as minus 3 by 2 x y square z. Okay, this is one of the component. So I am erasing all the ink again, so we can concentrate on the other. Omega x is by definition, so again this is definition, we need to calculate del w del y and del v del z. So let us look at w here, right. There is a y component, okay. So del w del y, right. So del w del y can be written as z square minus 3 y square z square by 2, and this is here, see here. Now we also need to know what del v del z is, okay. So del v by del z from here is going to be minus 2y square z, okay, correct, and this has been put with a minus sign here, so this becomes plus when coming here, okay. So I will erase the ink so that you are able to follow. So this is the okay. Pen. Similarly, omega y will be half, this again is a definition. Now del u del z, so it will be x y cube, right, and del w del x, so there is no x here, so del w del x will be equal to 0, and this has been shown here, this has been shown here, okay. So I will erase all this ink here. Okay. So we have calculated wz, wx and wy, and this gives us our 3 rotational components, okay. Now a stream function, what actually is a stream function? So in a 2D flow or a 2-dimensional flow, this type of flow considers 2 streamlines S1 and S2. The flow rate per unit depth of an incompressible fluid across 2 streamlines is constant and independent of the path, okay. So in a 2-dimensional flow we consider 2 streamlines S1 and S2. The flow rate of an incompressible fluid, for example water, across the 2 streamline is constant and is independent of the path, path A or path B from A to B in figure 9, okay. So this is the figure, this is 1 streamline, this is 2 streamline, okay. So you see this is A, this is B, okay, and this is path A, this one going to B, and this is path B going A from this to this, okay. So based on that, a stream function phi is so defined that it is constant along a streamline, and the difference of this streamline for the two streamline is equal to the flow rate between them. This is an important definition. So we will have a lecture on viscous fluid flow where we will be deriving everything from scratch, the equation of continuity to Navier-Stokes equation along with these streamlines. We are going to see there we will prove this. But for now, you have, as studied in your fluid mechanics class, a stream function phi is defined so that this stream function is constant along the stream line, and the difference of the phi s, that the stream function for the two streamlines A and B, is equal to the flow rate between them. Okay. Thus, phi A minus phi B is equal to flow rate between S1 and S2. The flow from left to right is taken as positive in the sign convention. So this is what we assume, that if the flow is from left to right, it is positive. The velocities u and v in x and s direction are given by, this is important. So if there is a stream function psi, okay, so u is given by del psi by del y, okay, and v is given as del psi by del x. Okay, this is the most important formula that actually you must be remembering. So the stream function phi is defined as above for two-dimensional flows only. It cannot be defined for the three-dimensional. For an irrotational flow, del v by del x minus del u by del y is equal to 0. This is we know from irrotational flow. Correct. Therefore, if we substitute v as what we saw, v was, you go back and see, v was minus del psi by del x, minus del psi by del x, okay, and u was del psi by del y. Now put v as this and u as this, you are going to get minus del square psi by del x square minus del square psi by del y square is equal to 0, and this is the Laplace equation. Okay. All right. So we can proceed to the next slide. There is something called a potential function. So in an irrotational flow, the velocity can be written as gradient of scalar function phi called the velocity potential. Okay, that is for an irrotational flow. Okay, phi is velocity potential. Therefore, u in terms of velocity potential is written as del phi by del x, v is written as del phi by del y, and w is written as del phi by del z. Okay. Considering the equation of continuity for an incompressible fluid, what was the equation of continuity? If you recall, del u by del x plus del v by del y plus del w by del z is equal to 0 for incompressible. Okay, correct? This we have already written. All right. And if we substitute these u, v and w here, what are we going to get? Del square phi is equal to del square phi by del x square plus del square phi by del y square plus del y by del z square, and this is again, tell me, Laplace equation. Okay, that's good. So we can proceed now. As I said, the velocity potential satisfies the Laplace equation for an incompressible fluid and an irrotational flow. Conversely, any function phi which satisfies the Laplace equation is a possible irrotational fluid flow case. So this concept will be used in numericals that you are going to solve. Okay. So any function phi which satisfies the Laplace equation is a possible irrotational fluid flow case. Lines of constant phi velocity potential are called equipotential lines. This is again an important concept, and it can be shown that these lines will form orthogonal grids with phi is equal to constant lines. This fact is used in construction of the flow nets for fluid flow analysis. That we can talk about it more later. Okay. There are people can also, I mean there are some authors which also define, instead of plus u is equal to del phi by del x, they simply prefer u is equal to minus del phi del x. It depends upon a lot of convention, but any of these formulas is correct. I would ask you to stick with this equation, u is equal to del phi by del x. Now the relationship between phi and psi for two-dimensional flow. Okay. So as we have seen, this phi exists for an irrotational flow only. Then u is equal to del phi by del x. Okay, velocity potential is equal to del psi by del y. Okay, and similarly v is given as, this is potential function, del phi by del y, and this is equal to, streamlines is minus del psi by del x. That we have seen before, right? So I'll erase this. Okay, so phi is constant along a streamline and phi is constant along equipotential line, which is normal to the streamlines. So by continuity equation, what we can write is del square phi by del x square plus del square phi by del y square is equal to 0 for 2D case. Okay. By irrotational flow condition, we can write del square psi by del x square plus del square y by del y square is equal to 0. Okay. That is, this is an important, you see, both satisfying the Laplace equation for irrotational flow condition, for continuity equation. Now we will see a practice problem. So there is a velocity potential for two-dimensional flow, which is given by phi is equal to x square minus y square plus 3xy. First we have to calculate the stream function, and then we have to calculate the flow rate between the streamlines passing through the points 1 1 and 1 2. So this question will actually clarify all your practical, if you have any doubt, but it's very simple to calculate. So we can look at the solution. So phi, first we write what is given to us. So we have written phi is equal to x square minus y square plus 3xy. Okay. So we are going to use one of the equations, right? U can be written as del phi by del x, this we know, and u can also be written as del psi by del y. Okay, correct. So from psi we del phi, we find del phi by del x is equal to, this will be 2x, right? This will become, I mean when we start calculating, this will become minus 0 plus 3y or 2x plus 3y, but this del phi by del x or u is also equal to del psi by del y. Okay. So we can simply integrate this to obtain psi, as it is. So, I will remove this. So, psi can be integrated to 2xy plus 3 by 2 y square, very simple integration with respect to y, plus not a constant but anything, because that is a function of x. Okay. Similarly, v is given as del phi by del y. So, we should calculate this. So, I will do this del, then I will remove del phi by del y is equal to, see, x will become 0, right, del in term, because there is no y term here. So, this will be 0 minus 2y plus 3xy will give 3x. Okay. This will become minus 2y plus 3x, and this is also equal to minus del psi by del x according to the definition, and you integrate this equation, and when you integrate this equation you will be able to solve this for again a psi. So, first let me remove the ink. Okay. And from 1, I mean this is yeah, so this is one of the ways that you can solve and then equate, but here what we have done is because psi we already have, okay, so we have calculated from this equation del psi by del x, and this came minus 2y minus f dash x, okay, right, and then in the end we have substituted it with this. Thus, f dash x is equal to, so see, okay, let me just go back. So, from the first equation we have calculated psi, okay, which was a function of x. Using this equation we have calculated del psi by del x. We got it minus 2y minus f dash x, and we have substituted this to this equation. Here what happened was minus 2y plus 3x was equal to minus 2y minus f dash x. Therefore, f dash x became minus 3x. Okay. There are two different ways, the other way was also fine. So, fx is, because we obtain f dash x, right. So, fx is minus 3 by 2 x square. Therefore, the required stream function will be, we substitute f of x from here into 1 to obtain 2xy plus 3 by 2 y square minus 3 by 2 x square. So, it can be written as 2xy minus 3 by 2 x square minus y square, same as this. Okay. So, now we are given the point. Okay. The second question was, we have calculated the stream function, right. Now, the flow rate between the stream lines passing through the points 1 1 and 1 2. So, at point 1 1 phi 1 will be, just substituting the value of 1 comma 1 will be 2 units. At point 1 comma 2, the phi 2 is going to be substituting 1 comma 2 in the phi that we have obtained, gives us 8.5 units, and the flow rate between the stream lines passing 1 will be the difference of this, and this is going to give us 6.5 units. So, I think with this we have concluded the fluid kinematics part, and it is almost time. So, I think we will start with elementary fluid dynamics, that is Bernoulli's equation, in our next class, and until then, goodbye, see you next class, bye bye.